factor here. So I will prove that the logarithm is enough to prove. That for every point, logarithm of just one factor, so it's 1 minus 1 minus t to the degree of x is equal to sum over all numbers m greater or equal than 1. So here I will consider only those points whose image is my fixed point x. So I will take all alpha, which is in f q to the m, to x, such that image of alpha is x, right? So this is a subset here, the fiber of this map. And I want to divide it by m and multiply by t to the m. Okay? So if I can prove this assertion, then we are done. Now, let's compute the cardinality of this set. So I have x. I have this point, closed point, so it gives me a map from the spectrum of k of x to x. And so here I am looking at maps from spec f q to the m. This is my alpha. And the condition that the image of alpha is x is equivalent to saying that this map alpha factors through this, right? So conversely, if I have any map from this scheme to this scheme, which is FQ linear, then I get alpha with this property. So so in other words, we have the following diagram here. So we have k of x, and we are looking at all possible embeddings. So this is FQ. Here I also have FQ. And so given an alpha with this property is equivalent to extending to finding an embedding of this field k of x into this larger field, right? This is my alpha. So how many embeddings do we have? So let's write it down. So the number of this is an exercise in Galois theory, right? Okay, so number of these maps with image of alpha equal to x. Gain is this number. So, well, there is a, the claim is that this is equal. Well, first of all, if the degree of this extension does not divide the degree of this extension, then there are no embeddings at all, right? So this is going to be 0 if m does not divide, is not divisible by degree of x. And otherwise, as Stepan said, it's just degree of x. Okay? M divides degree of x. Good. So it's now you look at this formula here. That's what you want to prove, and you just plug the result. Well, this this expression here in this sum. You see that only powers of t that are divisible by degree of x are survive. And what we have here is, well, I will write it down. So this is going to be sum over all, say, L. And what I have here, I will have t to the degree of x multiplied by L. So here I will have L multiplied by degree of x. And here I have just degree of x. And the sum is now over all L greater than 1. And that's precisely the logarithm. Good. So now I think I raise questions. Ну хорошо. Ну, я все-таки хочу на двух. Okay. So now I want to prove the convergence statement that I formulated and proved. So so there was a lemma that if you have any x of finite type over z, then zeta function which is product over all x in 1 minus norm of x to the power negative s converges for real part of s greater than dimension of x. Right? Good. So, well, in fact, the claim was that it converges uniformly on any compact subset here and also absolutely. So I'm going to prove this. The case where I actually need this, it's not difficult in general, and we leave it as an exercise for any x. So I will prove it for x over f cubed. And then, then we can write, make substitution as usual, t equal to q to the negative s, and write that zeta function x is equal to z of t as before. And so in order to prove this convergence, I will prove it suffices to show that if I take a logarithm of z of t and take d over dt t, then recall that this logarithmic derivative is equal just to the generating function of my numbers, of generating function for the number of points on my variety x. So this will be t to the. So it suffices to show that that this power series converges for t say from 0 to q to the negative dimension of x. So once we have this convergence, that's we will have. So this is this. It will follow that this power series defines a holomorphic function on this disk when absolute value of t is less than this number. Therefore, its integral also has this property, and therefore its exponential is a holomorphic function on the disk. So it will follow that z of t converges on this disk, and under the substitution, this disk goes to this upper half plane, left, right half plane. Yes. So let's see what we have to show here. So I claim that this statement is implied by the following. So in order to prove the convergence, we have to find estimate for the number of points. We have to prove that this number does not grow too fast. So I will prove that n sub m is equal to O of q to the dimension of x. So if I know that this number is less than some constant times this number, then just using the comparison with the geometric progression, we will be done. Yeah, thank you. Thank you. Of course, you're right. So this must be m. So, in order to do this, we may assume that x is integral. Because first we may assume that it's reduced, then we can treat each irreducible component separately, so it's reduced irreducible. And also we can assume that it's affine because we can cover X by finitely many affines. So if we can prove it for members of finite open covers, will be done. So, and affine. And then affine the affine space of dimension. Потому что на точки это не влияет. А точки такие же. Where this is finite. So since this is finite, the fibers of this map are uniformly bounded by cardinality. So that means that there exists some constant C such that the number of points here is less or equal than some constant C times the number of points on the affine space. And we are done. That's precisely the number that we have here. Good. So let's now we have so we defined zeta function. We see its relation with number of points. Now we can formulate the remaining weight conjectures. So there will be 3 of them. So let's see. I think I can do this. Yeah.
Do we really have a pole that's just applying real part of S equal to dimension of X, or is this not possible?
Real part. So do I have a pole? Yeah, I do have a pole. So it's not immediately. It's not at all clear from the proof, of course. So the conjectures. First conjecture, well, I stated it for affine varieties. So in general, so for any x of finite type over fq, z of x t is rational. Okay. So the second conjecture. Well, the other 2 conjectures are for smooth projective proper is enough though. Projective geometrically reducible. Irreducible, which means that X remains irreducible over no algebraic closure of this field. Okay, so then the second conjecture asserts that this function here satisfies a certain functional equation, and this functional equation relates its value at point t with value at 1 over t times q to the dimension. So, okay, I will put here dimension of x. And so here is maybe this will be inconvenient. So I will call this dimension z. So what is the statement? Let's see if I have room for this. So it's equal up to sign the following expression. So it's z of xt, and so here I'll have some power of t, and I will tell you what e is. It depends on x times q to the dimension times e over 2. So that's type of the functional equation that you'll have. And so I need to tell you what e. E, so it's an integer which is called the Euler characteristic of x. So e Euler characteristic, it's defined to be the intersection, self-intersection of the diagonal. So here I have x times x, and I have the diagonal, and there is a intersection pairing on cycles of middle degree, various integers, and that's what I take. So if you imagine, if you have a smooth, compact, orientable manifold over real numbers, then its Euler characteristic, which can be also defined as the alternated sum of dimension of its cohomology groups, is equal to the self-intersection of the diagonal. Okay. So that's some integer. If you don't know what the intersection number is, do not worry. So we will have an alternative definition of this. We'll talk about this more later. So, okay. So that's the statement. So what does it say? In particular, it's so this number e. This formula implies that so z of t is a rational function. So in particular, this statement implies that the degree of this rational function, right, the degree of its pole at infinity, the order of its pole at infinity, it's a ratio, it's a ratio of two polynomials. You can subtract the degrees of this polynomial. So it's equal to this Euler characteristic of x. For example, if you have a curve of genus G, then this number e is supposed to be what? What is the Euler characteristic of the curve of genus G? 2 minus 2g, right? If you use definition, the first definition of zeta function using this s variable, then this formula translates into a relation between zeta function computed at d minus s and zeta function at s, right? I will not write down precisely the formula here. So, as I already mentioned, this zeta function can be defined for any scheme of finite type over Z. So you can't even ask whether it's rational even over finite field. It's not this function which is rational. It's function in T is rational, but this is no longer a function in Q to the S, right? Unless X is over a field is a scheme of Q. So the first conjecture does not really make sense for an arbitrary scheme. But this type of relation, this type of this functional equation, you can ask whether the zeta function of any scheme over Z satisfies a a functional equation of this type. And for example, for Riemann zeta function, it's a well-known result of Riemann, right? There is a functional relation, a functional equation that relates zeta function at Riemann zeta function at point 1 minus S and zeta function at S. But even the statement of this would require the existence of an analytic continuation of this zeta function. So here, according to the first conjecture, this is a rational function. So it's a meromorphic function. Therefore, this is also a meromorphic function. So in particular, this makes sense. Unless you have analytic continuation, if S is very big, the real part of S is very big, the real part of this guy could be small, so it really doesn't make sense. So there is a conjecture which is very far from being proven that for any x of finite type over Z, the zeta function admits a meromorphic continuation and a functional equation of this type. This is a very deep conjecture. For example, it's strong enough to imply last Fermat theorem, even for for elliptic curves over Z. So okay. And now the last conjecture. The last conjecture is the following. So it's also formally stated only for it's over finite field. So it's the following. Suppose let's write. So we know that Z of again x is smooth projective, and let's write this as a rational function. So how I want to so let's write it as a product of polynomials, and I will write it in a so you remember I indicated Weyl's idea how you can prove rationality. The idea is to use Lefschetz formula for the Frobenius map from X to itself. And the Lefschetz formula involves traces of the Frobenius on various homology groups. So these are polynomials that correspond to each homology group. So you have homology in degrees from 0 to 2D. So, and some of them come with negative sign, some with positive. So, okay, 2D over D. So I want to write it in this way. Any rational function can be written. Well, I didn't tell you what is the statement yet, but the statement will be that this polynomials pi have very so if I write pi of t as product, factor it into product. Well, first of all, these are polynomials with integer coefficients. That's one statement. And if I write pi of t as product of over J of 1 minus alpha ij t. So alpha inverse are roots. Then the claim is that so these are algebraic complex numbers. The claim is that the absolute value of alpha ij, well, for every I, this is q to the power I over 2. So that's it. So I already explained that the first conjecture follows from the existence of a reasonable sort of homology theory for varieties over an algebraic closure of a finite field. And well, in the Lefschetz formula, the second conjecture is also has a counterpart in algebraic topology, namely it's an immediate consequence, will be an immediate consequence of the Poincare duality for that homology theory. The third conjecture, which is the most difficult conjecture, has no counterpart in algebraic topology. It's a statement about the eigenvalues of the Frobenius morphism that acts on the homology groups. It asserts that the eigenvalues, the absolute value of the eigenvalues of the Frobenius map that acts on homology group, have this property. And that's kind of the main reason why it's much more involved. It has no kind of simple explanation why this should be true. Okay, though it has a counterpart in complex algebraic geometry, algebraic geometry over complex numbers, and I will talk about this next week. Okay, so I think that's all about the statements. So, and now I want to explain proof of these conjectures for curves. So for curves, these conjectures were proven by Andre Vejle. That was one of his major achievements. It's really amazing, I think, very nice argument. Well, I want to change my annotations a little bit. So set up here is the following. So x0 will be smooth projective geometrically connected curve over Q, and G is going to be its genus. So the genus of the curve is by definition H0, I will say H0 of omega 1, and this is by definition dimension of the homology. So what are the tools here? So first I want to prove rationality. And the basic tool, you'll see that rationality follows directly from the Riemann-Roch theorem. So let's recall Riemann-Roch theorem. Well, I need combination of the Riemann-Roch and the third duality. So suppose I have a line bundle. So Riemann-Roch So we will see that the first two conjectures are direct consequences of Riemann-Roch theorem for curves, and the third conjecture, which is the most involved, is a consequence of the Hodge index theorem for product of the curve itself, for the surface. Okay, so what is Riemann-Roch? So suppose you have a line bundle on your curve, then the Riemann-Roch theorem tells you something about the dimension of the space of global sections of L. Well, more precisely, it tells you about something about the Euler characteristic, so dimension of H0 minus H1, or by third duality, it's the following. It's H0 of the dual line bundle twisted by omega 1, by the canonical sheaf. And so what is the statement here? So it's 1 minus G plus degree of L. So, well, how you, okay, that's what we'll use. So this has some important corollaries for us. So first of all, it implies that degree of the omega 1 itself, you plug here for L omega 1, then this is trivial bundle, so it's H0 is 1, and you get that degree of L is equal to 2G minus 2. And the second corollary, which will be the most important for us, is that if the degree is large enough, namely if degree of L is greater than 2G minus 2, then H0 of L depends only on the degree. This is 1 minus G plus degree of L. Very good. Хуже. Хорошо. Okay, so how to see the second claim here? How is it implied by the Riemann-Roch formula? So you need to check that this H0 of this tensor product is 0. Why is it 0? Yes, so the degree of this line bundle is negative, and what is the degree? It's number of zeros of a section minus number of poles. So if degree is negative, it means that there are no sections with poles, with no poles. Good. So now we are ready to prove rationality. Oh no, sorry, I need one more result. So theorem. So everything that I said so far, I promised to. So everything that I said so far is true for any curve over any field. So it's projective curve, but the field was not important. So here we have a curve over finite field, so x0 over fq, as before. And then the claim is that the Picard group of x0, peak 0, is finite. So this is a counterpart of the theorem in algebraic number theorem, Dirichlet theorem, which asserts that the class group of field of algebraic integer of the ring of algebraic integers is finite. Okay, so let's prove this. How to see this? Well, so what do we have? So proof. So we have Picard group of X, and we have the degree map to integers, and the kernel is peak 0 by definition. So we want to show that the kernel is finite. Now, so let's pick any L of sufficiently large degree with degree of L greater than, let's call it D, and let's assume that it's greater than 2G. Okay. Then by this formula here, H0 of A is not 0. Right? So it means that L has a global section, which means that L is equivalent, is isomorphic to the line bundle corresponding to some effective divisor. D is an effective divisor of degree D. So we see that every line bundle of sufficient, well, of this degree had this form, but now the number of effective divisors of given degree is finite. So what is the divisors? What is the group? What is the divisor group? So maybe I will let me mention. So here, so divisors on x0 is just the free abelian group generated by freely generated by closed points. Yes? What is the degree of a divisor? Well, for every closed point, we define the notion of degree, right? It's the number of elements, it's the degree of the field extension of the residue field over the prime field, over FQ. So the degree of a divisor is sum of the integers with, well, sum of divisors of closed points, or sum of degrees of closed points. Да. Точно. Сейчас of степень d равна, да, а мне казалось, что
Обозначение просто d.
Ага. Okay. Okay. Good. So that means that if you have a divisor of degree d, effective divisor of degree d, it's a combination of closed points, right? Whose, well, all the coefficients are definitely less than this number d, and all the closed points are defined over some finite extension of FQ of degree less than d, right? So then the fact that the number of effective divisors, right? So you can't have, of course, this set is infinite. But if you have a closed point of large degree, so the kind of, so my claim is that the number of effective divisors of given degree d is finite. And this follows from the fact that if you look at all closed points whose degree is less than d, less or equal than d, then this set is finite. And why it's finite? Because all these points come from points over FQ to the m, where m is less or equal than d. A number of, right? Good. So, so what we proved is that the Picard, the set of line bundles, isomorphism classes of line bundles of degree d is finite. Right? Just because every line bundle of degree d has this form, and you have only finitely many options for d. Now, and on the other hand, this is a this set is has a simple and transitive action of peak 0, right? So it's just preimage of d under the degree map. If it's non-zero, then it means that it has the same cardinality as peak 0. Okay, let's complete the proof. Now, now let's prove the theorem. First conjecture. So I will prove two results. So first of all, going to prove that zeta function is rational. But a little bit more than that. So I will prove that it has the following form. It has it's a polynomial f of t over divided by 1 minus t times 1 minus qt. And so what do we have? So this f of t is a polynomial with integer coefficients. And it has the following property. Degree of f is less or equal than 2g. Later today I will prove that it's precisely 2g. But now let's do this. So f of 0 is going to be 1. And f of 1 is the order of the peak 0. The class number. Oh, sorry, maybe. That's not issue. So another way of formulating this, the second statement is that if you, yeah. X0 is a curve over f. Yeah, so good question. So x0 is over fq. And x is x0 tensor fq bar. Yeah, sorry, yeah. X, in fact, hasn't yet appeared, though it will appear. Okay. So let's prove part A. So what is zeta function? Zeta function is I want to, so it's a product over closed points one minus 1 to the t times degree. So the first idea is to use the geometric progression formula, so expand it as a sum, and then multiply the infinite sums. So I will. So I claim that this is equal to sum of over all effective divisors on my curve. So D is a in divisor class group. Sorry, in divisor it's just a divisor. Divisor n x0 of the following expression. T to the degree of the divisor. So this is true by definition. Just expanded this geometric progression, multiply. Very good. So therefore, the zeta function is the generating function for the number of divisors, effective divisors of given degree. Now, the next idea is to kind of group together divisors, effective divisors that correspond to same linear equivalence class. So I will take, write it as a sum over all line bundles and here I want to take the degree, t. The degree of divisor depends only on the equivalence class, right? So it's degree of L. So now the question, that's really the main point of the argument. So what is how many effective divisors we have that belong to the equivalence class of L? So we want to, we are interested in effective divisors. Maybe I will. So the question is, what do we have to put here? So we are interested in effective divisors such that O of D is isomorphic to L. How many do we have of them?
Pick one and then shift the divisor of function in L of D.
Okay, so I think I need to write it down. So I will write it here. So we want to, again, so we are interested in D greater than 0 and such that O of D is isomorphic to L. To L. So maybe first question, how can we tell whether this set is non-empty, whether there exists an effective divisor with this property? Yes, yes. So so this set is non-empty if and only if H0 of X0 with coefficients in L, global sections of L, is non-zero, right? If you have a global section, then you can look at, you just take the divisor of this global section. It's going to be an effective divisor, and call it Z, and you have this, by definition. So every non-zero global section gives an effective divisor with this property. Conversely, if I have an effective divisor, then I can look at section 1 of this line bundle, right? It's a regular section with divisor D. So it gives me a global section of this. So what is the answer now? Okay, so it's this set, in fact, this is true over any field, is in one-to-one correspondence with the projectivization of this vector space. Okay? So, because, of course, if I multiply my section by a number, its divisor does not get changed. So I constructed map in both directions. It has nothing to do with finding fields so far. Now, so here we put the cardinality of this set. It's finite because we are a finite field now. So H0, well, this is my notation. Okay, this is H0, X0, L. Now, so I can compute the number of points on the projective space, as Stepan suggested. So I will write it as two sums. So one is going to be sum over all L of degree less than 2g minus 2. Well, of course, the degree is greater or equal than 0, so it's and otherwise this is empty. Here I will have something. This something is well, q to the h0 of L minus 1 over q minus 1 times t to the degree. That's what we have here is a polynomial, right? So then there is another, the remaining terms when the degree is greater than this number. And when the degree is greater than this number, this h0 depends only on the degree of L. So by the corollary of the Riemann-Roch formula, so degree of L is greater than 2g minus 2. So, and they'll have q to the 1 minus g plus degree of L minus 1 over q minus 1 times t to the degree of L. So we have two terms. So let's call this will be g1. Let's give a name to this. So this is g1 of t, and this term is g2 of t. So g1 of t is a polynomial with integer coefficients, and it is clear by definition. So what is g2 of t? You see, so this number depends only on the degree. So in order to I have to rewrite write again the sequence, the exact sequence that we had earlier. So we have the Picard group x0 of x0. We have pic x0, and we have the degree map. Right? So a priori, this sequence is not right exact, because we don't know whether there exists a line bundle of degree 1. For example, if we had a rational point on my curve, fq point, then of course this point would give me a divisor of degree 0, of degree 1. but in general, well, we need not have a rational point. Maybe we have, say, a point of degree 3 and another point of degree 2. Then the difference would be a divisor of degree 1. And in fact, we are going to see in a second that this is indeed the case, which is interesting on its own ground. So, but in any, so so the image here is a subgroup of finite index. So let's call this subgroup EZ. Any subgroup of a cyclic group is again cyclic. So, okay. So now let's rewrite this this formula here. So, so that means that the degrees that appear here are all divisible by this number E. So I will write it down. So this is going to be peak 0 of x0. This is so if I have at least one line bundle of degree d, then the number of such line bundles is, well, then the set of such line bundles has a simple transitive function of peak 0, so I have precisely this number of such line bundles. And what I take some, so the conditions are that ED is greater than 2G minus 2. And here I will have Q to the 1 minus G plus D times E minus 1 over Q minus 1 times T to the DE, right? So first, I observe that this degree must be divisible by E. So only these terms appear here. So then the coefficient here is the number of effective divisors of this degree, which is equal to the this number, the number of points in the projective space, by times the number of line bundles of this degree. And the number of line bundles of this degree is precisely this number. So you see that what you have here is this is geometric progression. You take sum over so you take sum over all D with this property. That's a summation over D. What is variable here is D. And then this is truncated geometric progression. In fact, I need in a sec. I need a formula for this. So I hope everyone can compute the sum. So it's peak 0 of x0 divided by q minus 1 times the following. It's q1 minus g times the following expression. Qt to some number, well, d0, I need to tell you what d0 is, over 1 minus qt to the power e minus t d0 e over 1 minus t. So this is the result of the computation of this. of the truncated geometric progression. So this is minus sign. So we already proved the first part of the theory, right? We proved the rationality. We proved the zeta function is sum of a polynomial plus this rational function. So now I want to prove the second part, and first I will prove that this number E is actually equal to 1, that this map is surjective. In order. Oh, yeah, so thank you. I haven't yet defined. So where D0 is the smallest integer with D0E greater or equal than 2G minus 1. Okay. So good. So now a corollary of this formula is that if you take the limit of the zeta function z of x0t, already know that it's rational, so the limit should exist. Well, it should be easy to compute, so t goes to 1. So, so I'm looking at the kind of residue of my zeta function at point t equal 1. So this does not contribute to residue. And what contributes to residue? Only this term here. So, so the residue is, well, first it's what is important is that this limit is, first of all, that it's non-zero. x0 of x0 divided by e to the q minus 1. Okay? So this is what we know. Now, so next I will prove that e is equal to 1. And in order to do this, I will use the following trick. I will define x0 prime to be x0 tensor fq to the e. And I think of this as a curve, geometrically reducible curve over this new field. Then, so here is a claim, which is claim, which holds for any scheme over FQ. It's formal. It's similar to the first claim that I proved today, that z of x0 prime, z to the e, is, so the zeta function of this scheme is related to zeta function of x0 by the following formula. It's equal to the product, I equal 1 e, of zeta functions of x0 computed at roots of unity. So here epsilon is exponential of 2 pi I over E. Yeah. So I will leave this claim as an exercise. Again, it has nothing to do with curves. It's completely formal. And now we can, let's apply this. Well, in our case, using the formula that I just erased, we see that well, this function here is actually a function in t to the e. Because, well, it's clear, because only divisors of degree whose degree is divisible by e appear in this infinite sum. Right? So that means that, so since this function is a function in t to the e, so all these factors here are the same. So we have that z of x0 prime t to the e is equal to z of x0 t this power. Yes? So now this has a simple pole. Right? So I know that by applying the argument that I just gave to this curve over a larger field, we know that this function has a simple pole when t equal 1. Да, и того факта, что вот эта z-функция, она на самом деле функция от t в степени i. Почему? Потому что просто ну, это некоторая производящая функция для дивизоров эффективных. Они у них всех, вообще у всех дивизоров степень делится на i. Okay, so at t equal 1. But now, what is the pole of this guy? Right? So this function has a simple pole at t equal 1. That follows from this statement, applied to x0 prime. But if I have a function that has a simple pole at t equal 1, if I substitute for t to the e, it still has a simple pole. Now, what is the pole of this guy? So we just proved that this function has a simple pole. So when I raise it to the e power, I get a pole of degree e. Okay? So therefore, e is 1, and I will write it here. E is 1. And that proves the second statement. So the second statement was that precisely that this limit is equal to the number of the order of the class group, the order of this, over q minus 1. So once I know that e is 1, we are done. Okay? So in particular, using the zeta function, we proved that there exists a divisor of degree 1 on any curve over a finite field. Okay, I'll stop here. Да. Где мы использовали геометрическую неприводимость? Ну, сейчас. Сейчас. Нигде. Нигде. Сейчас. Нигде. Можно было не предполагать. Спасибо. Сейчас. Или все-таки... Сейчас. Нет, мы использовали. Простите. Конечно, мы использовали. Мы использовали, что да, Дима, я извиняюсь. Значит, мы использовали формулу Римана-Роха. Например, мы использовали то, что глобальные... Значит, мы использовали теорему Римана-Роха. Если геометрической непереводимости нету, то формула Римана-Роха, как сформулирована, неверна. Например, она неверна для тривиального рассвоения. Вот у меня есть кривая на dfq, которая не является геометрически непереводимой. Значит, но сама, может быть, она непереводима. Ну, значит, может такое случиться, что глобальные функции на ней это большее поле. Это не обязательно, например, можно было бы что сделать? Можно было бы взять какую-нибудь геометрически непереводимую кривую x0 и умножить ее на f q в квадрате. Вот, пожалуйста, вот она по-прежнему, вот если это геометрически непереводимо, то тензорное произведение это по-прежнему будет неприводимая кривая над f. Она уже не является геометрически непереводимой. На самом деле все геометрически приводимые, они так устроены. Они происходят из геометрически непереводимой вот такой странной конструкции. Но какие здесь глобальные функции? Глобальных функций здесь больше. Здесь вот глобальные функции. В результате, значит, из-за этого в формуле Римана-Роха там будет поправка. Там нужно будет все умножать на степень поля констант. Вот на x0 есть глобальные функции. Это не обязательно одномерное векторное пространство на dfq. Оно имеет какую-то размерность. Вот на него нужно будет умножать. Еще вопросы? Давайте, у меня тут есть некоторый телеграм-канал, который, давайте мы это устроим, обсудим. Во-первых, сейчас другой курс начинается, я хотел, это длинное обсуждение, давайте мы сейчас, значит, я попробую произвести опрос с помощью этого телеграм-канала.